Hey guys, I'm going to talk about Kruskals' algorithm. I'm going to start talking a bit about some mathematical notation and formalism, and then I'm going to show 3 examples of the algorithm. It might be a bit confusing with the notation. If you don't understand it, don't fear. Just wait for the examples, and it might make sense afterwards. But in my opinion, the most important part is actually the examples. So the formalism is actually just to help you. If it doesn't, don't worry. Yeah, okay. So Kruskals' algorithm takes some graph G, some connected graph G with weighted edges. So we have this graph has some vertices, it has some edges, and it has some weights, right? The vertices and the edges can be represented by sets, and the weight is actually a function that assigns some integer, some number actually, but in this case it assigns some integer to each edge. So you see each edge has an integer representing its weight. It could also be like rational numbers, but in this example we just have integers to simplify it. And we have a single example of a negative integer. Yeah. Okay. So what Kruskals' algorithm does is it takes one of these graphs, right, and it produces a minimum spanning tree. So what is the minimum spanning tree? A minimum spanning tree is the new graph, so we produce a new graph, G1. And this graph has the same vertices, right? It has a new set of edges, so that would be, we call it E prime, and it has the same weight for these edges. It just doesn't have all the edges. The minimum spanning tree, in the minimum spanning tree, all vertices are connected. So we can't just so we have that E prime, the edges of this minimum spanning tree, is a subset of the edges in our original graph, right? But we can't just discard all of them. We have to. It has to be so that all vertices are connected. Also, we want it to be so that the sum of the weight for all edges in the minimum spanning tree is minimized. So we want to minimize this. Okay, so that's a lot of talk. That's a lot of math. Let's look at the example and make sense out of all of this. So we look at this graph, and what we do is we want to find the edge with the least weight. That's minus 42. Okay. Then we want to find the one with the second least weight. That's 1. We continue doing this, right? We want to find 2. We do that. We want to find 3. Find another 3. Another 3. Look for an edge with the weight 4 right there. And I can't seem to find anyone with the weight 5, so we move on. And okay, so if we want to minimize the weight, right, we can't have any cycles because, yeah, okay. So actually that's also part of the minimum spanning tree definition. We don't want any cycles. So if we choose this, we would break that. Yeah, so we don't want any cycles. So we can actually say, well, we can't choose this edge, we can't choose that, we can't choose that. At this point, yeah, okay. So we move on, we look for any 7s, we can't find any, so we look for 8s. And we move on to 9. So we can't choose this 9 because that would produce a cycle. We look for 10s and 11s. Can't take 12. We look for 13. And I'm just gonna exclude something. We can't take that. We can't take that. We can't take that. We can't take that. Can't take. You can't take any of these actually. So we just need to connect S and B now. So we want to choose the least of these. We take 11, and we want to take the least of these two, and that's 24. And now we're actually done. So this is the minimum spanning tree. And you see, like, well, this graph has the same vertices as before. We have all the vertices as we had before, and the edges is like a subset of the edges we had before. And if we sum the weight of all the edges, we have made the graph so with that it is so small as possible. As small as possible. Yeah. Okay, so I'm gonna move on. I'm gonna try to speed it a bit up. So also for the next examples, all weights are gonna be distinct. So we're not gonna have like the same weight several times. So it's going to be a bit faster to do. I won't have to, like, if I take one, I won't have to look for one because it's not going to be there more than one time. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, we can take that one, that's okay. No cycles yet, but if we take 12 right now, we would have a cycle, so we can't do that. I'm just gonna clean a bit up. We can't take 3, we cannot take this one either. So we're at 12. Let's look at 13. 13, where are you? Yeah, that's legal. That's legal. We look at 14. So yeah, we can do that. We look at 15, that's illegal, so I'm just gonna, yeah, we can't take any of these that will produce a cycle, right? So we look at this part. Now we want to have the least one to O is 17, the least to R is 26, and the least of these connecting the two graphs is 20. And the least from either of these to T is 25. Now we're actually done. Okay, for the last one, we just start at 1, 2, 3, 4, 5. Whereas 6 is here. Yeah. 6. We look for 7. We can't take 8, we can't take 9, we can't take 10, 11, 12, 13, 14, 15, we can't take that one now. 16, where is 16? There it is. 17, can't take that. Just going to exclude, so we can't take that of this or this, we can't take that one, and we cannot take 9 or 10 or 15, 8, 13, 19, 18. Okay, so what we want to go to M, and the edge with the smallest weight is 26. We're going to go to O, and we take 27, and we're going to go to D, we take 21, and we're done.